I hope it starts. Okay. All right. Is the question clear? So you see this text, and there are these four theories that we talked about in the last class. Um, Gestalt theory. Parts of the entire configuration derive their meaning from the whole and not only its parts. So you are seeing the overall pattern or the form to be able to understand it. Template matching, you match the sensory
So your
stimuli.
slide is not good. Only the first slide is visible. Introduction to psychology.
Oh, okay. All right. Yeah, sorry. So this is the slide I was
Yes.
referring to.
I'm-
So this is what we stopped in the last class. So you were able to read it. Now we have to explain how we are able to read something like this, which is crazy because none of these, most of these are non-words. Non-words are which are not technically a word. How are we still able to read these non-words as if they are a word? Uh, we have to explain that using a combination or a single of these four theories. So first one is Gestalt theory, where parts of the entire configuration derive their meaning from the individual parts, because you are perceiving the whole and not individual parts separately. Template matching is when you're matching the sensory stimuli that you're seeing with this mental form. It's a one-to-one matching, which means every single stimuli must have a corresponding mental representation. Prototype theory means prototype theory says that you are matching a sensory stimuli with not all possible mental forms, but one single idealized mental pattern, which means that it's like a many to one. And the fourth one is feature analysis, where you're working your way from bottom up and you're analyzing different different features to eventually build up the form.
So what would be the difference between template matching and prototype?
Um, Template matching and prototype is, for template matching here, if you see this example, for template matching, if I have to understand that this is an A, or all of these are A's, if I have to understand that, then I have to have templates for each of them. Any small deviation will result in a non-match or a failure of matching, because I'm matching one to one. If I have a template for that, then the match is successful. If I don't have a template for match, that it's a failure. But for prototype, the idea is that you have one idealized A, let's say here A, and we allow different kinds of levels of error from this. But that slight error from my idealized A will not result in a non-match, because I have one single prototype. That's why it's called prototype theory. But, or maybe I have more than one prototype, but not all of them. So let's say I have one prototype for big A, one prototype for, let's say, small a. Deviations from this big A and small a, like this one and this one and this one, I'll still, or this one, I'll still read as an A, although they deviate, because I'm able to accept that amount of deviation or that amount of error. Whereas in template matching, I'm not able to accept any errors. It's like a very hard coded match between the stimuli and the mental form. But for prototype, I have one or two or a bunch of them, but not all of them as prototypes, and differences from the prototype is acceptable. That's the difference. If you're saying something, you can just raise your hand and speak instead of writing in the chat if it's an important point. You have to explain this thing. Which of these four theories, either one alone or a combination of them, are able to explain how are we able to read this?
Sir, I guess prototype theory, from the prototype theory we are able to read, because there are certain errors which our mind thinks that is all right, we can read. So according to me, it is prototype theory.
Okay. Anybody agrees or disagrees?
I think the Gestalt theory is more good in this case.
Can you explain in what way?
So because even if the words are, even in the if the alphabets are jumbled, the whole is still like eligible. For example, like in because the spelling is wrong, but the parts are the same, but we are still able to make that the word is because. That is the whole is different from what the parts portray.
Yeah, very good. Any more joiners or something else to add? Anybody disagrees that it's prototype or
So
it's gestalt?
it is
Yes, go ahead.
more like Gestalt theory because in this paragraph where the spellings are jumbled that don't make sense grammatically, but we can understand and see clearly that the last and first letter of words are in the same place in most of the words. If they were not there, we would not be able to read it so simply. Just the spellings between the first and the last letter are jumbled. So I think our mind perceives the spellings of the word from the first to the last as a prototype. So I think it is a mixture of Gestalt theory and the prototype theory.
Okay, so we have two candidates, gestalt and prototype. Anybody wants to add something or subtract any of these two out? So think about it. For prototype, what kinds of prototype do we need to have for us to be able to solve this task? For those who were saying prototype, what are the prototypes?
The prototypes are stored words in our brain that we
Okay.
have acquired through linguistic capabilities of the language.
All right, fantastic. Yeah, so you are all, well, you are right. And in fact, that is why the two letter or three letter words remain as it is, because you can't do anything if you keep the first and the last digit constant. This, by the way, you can also train a neural network to read, and people have done that at Cambridge, which shows that you can model this kind of noise or acceptable noise of reading in computers also. So it's fine if there are certain spelling mistakes, the computer is still able to read that same text, and
But
it's
U
not going to
has
comprehend.
been changed.
Oh, U has been changed.
Sir, it is still readable because it is just a three-letter word. So
It's
it
a
is
three-letter word. Yeah,
so it is
and
quite
it's
easy to handle that kind of exception.
yeah, and it's
In
also
the
very rare.
in the larger words such as phenomenal, we would not be able to guess such a large word if P and L were not in the place that are here.
Hmm.
But does presence of do just behind you help us to recognize that it should be you? Because it has been taught us from the early learnings that you is
Yes,
always succeeded after do.
Mhm.
yes, sir. Some grammar syntax also help this grammar syntax.
Yeah, absolutely. In fact, there's a whole area of research in psycholinguistics which tries to study how people read this line. And this is what people find. I mean, people basically go about reading it, even if you look at where they're looking at, they don't even, I mean, if you put this YUO in any other completely um, in other sentence which has no other spelling mistakes or spelling changes, people might not even stop over why you, or they'll just read it as you and move on. So all of these things, now you see. Okay, so now let's go even more further. What is the first, now that you know a little bit about perception, can you list out exactly what are the steps involved or could be the steps involved for us to read this? Start from the very starting point. most rudimentary processing, what is the first processing that's going to happen?
So the color difference between the background and the letter will be but will create a stimulus,
Yes, very good.
and that
Then,
will be received on our retina.
no, how will we understand a letter?
Letter.
So we'll think of what we have learned before and try to relate the
No, how do
pattern.
I, yeah, not that high level. I am talking of more biological, I mean, much more low level stuff. So, how do I know this is D?
We can, there's a gap between the next letter just by the basis of what Akash said. The color of the background and the letter is different, so we can see that the boundary of D is this, the boundary of O is this. So there's a gap between them. So this is one single individual letter.
Okay. And how will this letter be understandable to me? Start from the retina.
So it will be converted into electrical signals, which will be carried on to our brains through the neural network.
What will be converted?
The
And
image of the
2D
letter.
image.
Which one? Only this line or this whole D or do or this whole thing?
No, the entire screen is being formed as an image. We just focus on one specific part at one time, and then maybe.
Maybe that is part of today's talk, which is about attention. So, what do we pick out as information from here? That's an interesting question to ask. Clearly, we are not reading everything at one go, right? So,
Because when
although,
we sir, because when we are focusing at this paragraph, even though the entire image of the screen is projected, I can't focus like on my laptop. I still can't focus on the taskbar which is below. The main attention is only on this paragraph. So even inside that image, we are focusing mainly on this paragraph.
So because the image is forming on that part of our retina that has lot of cones and rods, so they are actually focusing more on. We are actually focusing where the image is being prominently formed. The
okay,
taskbar will be formed on the other part of the retina where there are less number of uh, receptors.
yeah. See,
Sir, sir,
no one.
maybe,
1 minute.
sir,
So, first of
maybe,
all, okay, you go ahead.
no, sir.
No, tell me, then I'll tell.
Okay. So actually, in the previous class, we have also talked about like the cells in our retina are actually inhabiting the other data that takes the other retina cells. So maybe from this theory, we can also say that we are able to read this.
No, I mean, I was asking something much more simpler. So, I have to first detect this is an edge. Who will do this? Or where will this be done? Not who will do this. That's a bad question.
First of all, we will sense the word by our senses, eyes. Then it
The
will go.
whole word do.
Yes, sir. On which we have focused more.
Okay. Right.
Then
And
it
then,
forms an image on the retina of our eye.
hmm,
Then it send the signals of generally the whole slide into a brain. But we have focused more on the word do. So it will more clearly visible than the other words.
mhm. All right. So, once we have do or we have focused on do, so which part of the brain will be able to detect which is the edge and which is the curve for us to be able to eventually realize that this is D and this is O and hence is do?
So I think we will use template matching to detect this as do as D and O and then combining it to be do.
Yeah, that's right. No, so template matching is a theory, is a perceptual theory, but I'm saying even to be able to figure out that this is D and this is O, there has to be some pre-processing that is going to happen after this information is carried from your cells in your retina to your brain. Brain means your visual processing, which is your first entry level into your brain. For you to detect that this is an edge, so edge detection, if you remember, I was saying in the is one of the rudimentary and first things that happen. So you first detect there is an edge, and this edge detection happens inside the brain as the first level of processing, visual processing. And from edge detection, you get to pattern detection. Here you detect the pattern to be this, based on, of course, the image that is fed from your retina. Then you get to do, and then all of this stuff that you're saying comes into force, which is template matching, and figure out that you have templates for, oh, you said template matching. The other person said prototype matching. And of course, there's also a lot of inputs from the whole, which is the Gestalt principles. But
Sir,
should it be template matching or should it be prototype matching? Yes, sorry, go. Yeah, tell me.
Sir, in I was still in the previous question. I was thinking maybe we can see the edge. Maybe the edge detection is done on the basis of how contrasting the surroundings are. As in, this is white and black, so we can easily differentiate due to the high contrast that this is one part of.
So yes. So if you want the details, perception typically has two kinds of filters. One is a high contrast filter and one's a low contrast filter. Most of the time, high contrast filters try to give you edge detection, and that is implemented in the V1 area of your brain, which is where your optic nerve directly hits the first spot. Then you go to low level filters. This is a computational term, of course. So high level and low level filters are implemented through neurons in the brain, but mathematically they are high level and low level filters, which happen in which is called very early visual processing area, which is also called V1 and V2, which is just behind your brain and the start of the brain. I don't know if we had some slides about that sometime back, yeah, before this class perhaps. Okay, so I think you all got the sense of it. So let me move to the next part, which is the focus. But even before that, a little bit about patterns, I think are important. So these are the things that we already know. So we are able to recognize familiar patterns like faces of friends, as we saw, or keys. We are also able to operate on unfamiliar patterns or objects like an unusual A or a new kind of a dog or these non-words as you were seeing. We are also able to figure out that there's an object even though we cannot see it. It's partly hidden. And we do that all very dynamically and very, very quickly. How is that possible? I think there are two aspects that we have to talk about a little more detail. One is the search mechanisms, and the second is the focusing mechanism. So you were already talking about focus, where you are looking at or where you're focusing. Now there's a word called attention. So where you focus your attention is from where you get the maximum amount of information. So you take one example here, which shows the figure ground principle in action. Can you understand what this is?
A.
It's a poster with a hole cut out in it.
Is it a hole or is it a print of a?
It
Sir, it is
can
a
be
hole because it's
if
a
we look
shadow
at it
is
So in
there.
the shadow, we can
Yeah.
easily see.
It's a hole.
Yes, sir. In the
It's a
shadow.
hole.
Yeah. Now imagine if we would not have the jungle in the background, then it would make your job much more easier. It always takes a little bit of time, and some smart people like you all figure it out from the shadow, but it's not so obvious. And this is one great example of having used figure ground principle in advertising. This is a billboard for Wrangler jeans, and they use it so well. Of course, this is cutout, but this cutout automatically drives attention towards it because of the figure ground principle. So here now here you see that a perceptual principle of the figure ground segregation is used by a company in real life for a billboard for driving your attention towards it. Right? This is how you see practical implementations of psychology in a whole lot of advertising and management and consulting areas. But this is really, I just love this example because it stumps most people, and it stumps most people because of the figure ground principle. Otherwise, it won't. Right? So if this would have been a wall, there would not have been any issue. This is another example. As you know, this is a logo of Unilever. Do you know what is it made up of? I'm sure all of us know or have seen the Unilever logo. Have you ever wondered what is it inside the logo? No? So it turns out that there have been lots of mergers and acquisitions and also their own product brands, and most of them did have a symbolic representation, which was their own individual logos. Now this bigger Unilever logo essentially is a set of multiple logos. One classic perceptual theory in action. What is that? Out of the ones that you just studied?
So, sir,
Guessed it.
looking at the whole or looking at part.
Name?
Guessed it, Siri.
Gestalt.
Gestalt theory.
Gestalt theory. Gestalt. Sorry.
Gestalt theory also has multiple principles. Any idea which principle that is? We talked of closure, we talked of similarity, we talked of continuity, completeness. What else is there? Okay, so let's explain. Okay, maybe some people are not following. So how is it? Which is the one that you're saying, and why are you saying that? Can you explicitly say that? You're right, but just explain it for your friends, and others can also chip in. Which is the first one? Which principle in under Gestalt theories? Sorry, I can't hear anything. Are you all saying something or what?
So continuity, we can say that
Continuity.
all the small parts that have been placed are very close to each other, and as a whole they tend to
Make up the
give us a feel of U shape, U alphabet.
Right. Fantastic. So one is we see a principle of continuity in action. What's the other one?
So I think closure can be used here because it is kind of closing it as you. The boundaries are somewhat closing it as you.
Yeah, very good. Um, does this remind you also of the illusory contours that we saw, and any similarity, or rethink about how that might also be have utilized? Is there a contour?
Yes, sir, the boundaries are not complete, but we are actually trying to complete it to get a feeling of alphabet U.
Yeah. Great, right? So you see that people are already using perceptual theories in the real world with great brands and big advertising campaigns. And we are just formalizing how these things are already working in life. It's not something new or strange. We are trying to explain it better, um, so that you all are not going to do, folk psychological talk or commonsensical talk, but get a little more headway into it. Okay, so I think we got enough of an exposure to perception. Let me now take you all to attention. Now, to go to attention, I think there is one or two at max fundamental processes. So the first fundamental process is search. There are different kinds of search you could do, and a couple of them I will show what they mean. You can search for features. You can search for features, multiple features instead of one feature. You can search for things when, depending on whether they are moving. So something is moving together also gives you a kind of a pattern. which again comes from Gestalt psychology, principle of common fate. If all these things are moving in one line, that helps you detect it better because it's based on motion, and you can search from your memory or search based on your memory. Now, to be able to search, you have to attend to the stimuli or the world. So there are two kinds of attending, two kinds of aspects of attending people typically talk about. One is orienting and the second is selection. So first you have to orient, which means you have to focus on or towards a certain stimuli. So that's what orientation typically does. It can be endogenous, which means that I voluntarily focus on something, or exogenous, means the stimuli itself has certain properties like color or a dazzling light, or a weird thing that automatically drives my attention towards it. So if I'm attending on my own, from my own desire to attend to it, it's called endogenous or voluntary. If I am attending to it because of nature or properties of the stimuli, then it's called exogenous or automatic. After I've attended to it, I have to select the most important or most valuable information according to me. That is what attention does. So what happens most of the time? Typically, it's endogenous attention. Again, to remind you, endogenous is when I'm myself attending to something. So it's voluntary attention. So because many of our tasks are, because many of the stuff that we do are task driven or goal directed, automatically depending on the goal, you will select certain kinds of information. Say for reading, because you have to read, you will select a subset of words so that you are able to actually read it. And similarly, if you're searching for a key, you have a goal to find a key. Or if you're searching for a friend in a crowd, you have a goal of searching for a friend, and likewise. Also remember that if you look at your eyes, there is something that you can see right there in front of you based on if you're staring at it or if you're looking exactly at it. So that is called foveal vision, which is to do with around the periphery of your eye. And then this is called parafoveal vision, which is at the periphery of your eye. So you would perhaps look at this part with maximum clarity, whereas you can still somewhat see what's there, but you can't really figure it out. So this will be parafoveal vision, or stimuli in the periphery. We process a lot of information based on our own needs, but also based on covert sensory stimulations and exogenous orientation and task goals. Exogenous, automatic. So whenever you have certain kinds of bright light or bright color or this and that, they are all exogenous attention. To be able to understand this perfectly, or to a reasonable extent, let me remind you that brains, these are three kinds of brains. This is a human brain, this is a brain of a monkey, which is a macaw, and this is a brain of a rat. And you see that this is the primary visual area I was talking about. So after your eyes, your information directly taken to your primary visual area. And you see that this is similar across humans, macaws, and rats, somewhat similar. This is also where your first initial image processing happens, including edge detection and all. But that's not all that's required for you to attend. You need other things. You need here, this is called the superior parietal cortex. This is the inferior one. Superior means on the top, inferior in the bottom, nothing inferior and superior in the way it's used in English. This is a neurological terminology. So superior is thought to be, or conceptually, something which is at the top, and inferior is something at the bottom. Then you also need to move your body, or you also need to move certain muscles. So here, that's why you need somatosensory. Soma is body, sensory is senses, somatosensory is sensations to do with the body. So this part of your brain codes for somatosensory information. That also you need. And you need the primary motor cortex. So you need the primary motor cortex to actually move your eyes and many other hand and stuff. So all of this put together is what helps us perceive, attend, and act. It's not just about our eyes. It's not also just about our vision, our visual area. Now, what was that? If you look in more detail, you see that attention typically constitutes of um, three things. One is it has to alert you, so it's the process called alerting. Once you're alerted, you orient, which means you detect a certain subset of your environment to have higher value, and accordingly you look at that side. You orient means you move your eyes towards that area, or even if you're sitting, you move your ears attention. So you don't move your ear, you orient your ear, or you orient your thinking to hear something, let's say coming from a left side or right side. And then you have executive control, which enables you to decide how much information has to be taken in, where you have to attend to next, and how to move certain things, including your eyelids. So if you see that alerting typically happens in the frontal area of the brain, which is the right frontal area, just here, between your two eyes. Executive attention again happens in the frontal area here. Orienting, for you to move your attention, again, you're not moving your ear, you're orienting your auditory field, or you're orienting your visual field to pick up information. That happens in the in the primary visual cortex. Sorry, but in the primary motor cortex, and also in your parietal cortex, both the superior parietal and the inferior parietal. Additionally, because you need to orient, you have to alert yourself. And if you alert yourself, you also need to have a tap on the parietal cortex here. So that is why you see alerting is happening both in the frontal area and the parietal area. Both parts of your brain are involved in it. For executive controlling, typically it's happened in the frontal area. And for orienting, which means to attend, you need to move. And here you are moving your eye field, which is coming from your motor cortex. You also need your parietal cortex. And this is deep within the brain, which is called superior callosum, which is kind of helping you um, to disregard certain other aspects of the stimuli or certain other aspects of the environment to able to pick something which is most relevant to you. Now, this is an example of how attention operates. Of course, you don't see this red and purple things, but if you would, then this is what you would see. So here you have this person alerting or orienting the auditory field towards what this person is perhaps saying or doing. These are visual orientations. So this person is looking here and here. This person is looking in the front. This person is looking in the front. This person from here is looking here and somewhere else. So looking, if you look at something, you may not attend to it. I can just look at your face, but I might be thinking something else. So looking is not attending. I might not look, but still attend to it, which is what this guy is doing here. Not really looking at this person, but orienting the auditory field to hear what this person is saying. So looking or perception is different from attention, because you may look but not attend, you may attend but not look. Similarly, you might hear but not attend, you might attend but not hear. All right, now these are examples from visual perception. So this is a task which is to search a feature. So if, let's say, I want to search a gray circle, then it's just out there. So it's only one feature I match, no match, only one single. So it just what is called pops out. Whereas for conjunction search, here if I say any gray object, so I have to match both the color and the shape. And hence this, all are successful matches. As an example, here you see that in a whole pool of green circles, obviously the red pops out if I'm searching for one feature. But here it's not so easier to pop out, because there are colors which are similar to red, and hence it makes the task more difficult to. These are called distractors, by the way. if you plot a line, you will see that the total search time that's required for me to say whether the target exists. Target is, this one is a target. So let's say my target is to find whether red ball is there. If it is there, press the left arrow key. If it is not there, press the right arrow key. Let's say this is a typical task. So here, if I do this task, this is going to pop out, and hence automatically um, I'm going to, get the same amount of time. But here it's not going to pop out. And if you have a distractor, then your search time linearly increases with the total number of items on the screen. So if you would have, let's say, 4 items, the time that's going to require is going to be less compared to what is going to happen now. Now, this is, any questions here? No question? All right. So the second thing is conjunction search. Yes.
Sir, you told in the previous slide, like we can attend something but not look.
Mm-hmm.
Sir, how this is possible? Like for this person, like this is looking at another person but attending this person, which is just almost behind him. So how is it possible to look a person without attending a person without looking?
If you don't, so that's typical. Many times we do that. We don't really look at that person, but we are close to the person, so we are able to hear or even get a glance at that person visually. That's what I meant
Okay,
by,
okay. Other, you mean like other stimulus type of thing?
no. So
Other than
here, for example, this person might be attending to what this person is saying, okay, but not looking at this person.
okay. I understood, sir.
But it will be forming the peripheral image not clearly if he is not looking at him and paying the attention towards him. Then it is forming a peripheral image on his mind.
Yeah, that it will, of course, and that we can't do anything about it because of the way our eyes are structured. So you basically have a foveal vision and a parafoveal vision. The foveal is what is in your eye field, and parafoveal is what is plus minus 20 degrees from your eye field. And similarly, you have auditory fields also. You can hear something but not attend to it, or you can attend to something and while hearing some other stuff, or even fake not hearing it, but you're attending to it, which is what we do when we eavesdrop on what other people are chatting about.
Sir,
Yeah.
so suppose that person that was not attending visually but was attending auditorily, he had two person on the left, one standing on the left side and one on the right side. Could he be able to manage his attention to both, or he can at once attend only what a single person is saying on his left side, or a single person on his left side? Can we attend at the same time both or not?
So it depends on the content of the message. So there is work that was done by Annie Treisman, who was a professor at Princeton, a lot of work actually, where they try to see how much you can attend when I have one message which is coming to both of your ears and another message which is in the background, or one message coming to one ear and another message coming to other ear, or other people chatting about stuff when you are attending to something else. So it turns out that there's something called the cocktail party effect, but there's also something called dichotic listening and many other kinds of jargons which I don't want to get into right now. But the basic bottom line is that if the content is of completely different physical properties like pitch and prosody and whatnot, or if the content is completely of different semantics, which means one person is talking about marks and one person is talking about a cricket game, then I can get some part of it, though I typically have one predominant channel through which I hear most of it, and one non I mean, not the primary channel through which some other information can get in my ear. But if they are talking of the same topic, or if the characteristics, physical sound characteristics are so similar to both of, I mean, very similar to both of them, then what I can get from my non-dominant channel is very low. And that's typically what you would expect in a signal detection paradigm also. Okay. All right, so let me move to the next one. So the first one is feature search, which is essentially searching for one single feature. You can search for only one feature, or you can search for more than two features. Here is one example for that. For conjunction search, so let's say the task is you have to find this T, which is an upright T, which means that an inverted T, although it's of the same color, is a distractor. It's not, this is the target. An upright orange T is the target, which means the opposite, the non-upright or the inverted orange T is a distractor. The upright blue T is also a distractor. Now here, see what's happening. I have to search for both the pattern, which is a T, and also for a color, which is orange. Now only when both of these two match, then it's a success. The problem is because the color overlaps, or even because the structure overlaps, I am going to find it harder. And that shows up in my response times. So let's say here you have one place where you have to find anything which is of color blue. Now this again is a pop-up. Irrespective of how many other distractors I have, my performance is going to be same, because this is always going to pop up, whether you have 10 zeros and x's or whether you have 200 of them. It will not have any effect on my search time. However, if I do conjunction search and I say search, the target is of color blue and letter X. Now here I have competition. There are more items if letter blue, which are distractors, which is all the zeros or O's. And then I also have to search for letter X. So now I have red X's, which are again distractors. So only a blue X is my target. Now here what happens is, depending on the display size, the time for me to search for it keeps on going higher. So a two-feature search algorithm, or two-feature search, not algorithm, two-feature search behavioral response or an experiment is such that you will see that the reaction time is keeping on increasing depending on how many items you put on the screen. However, for single feature search, because of pop out here, the time it takes is going to be constant, irrespective of the total number of items that flash on the screen. Is this part clear? Any questions on this? Okay, if not, then let me show you.
Sir.
Yeah. Yes.
It means as soon as we will increase the number of characteristics in our search, like color, letter, and if we increase more, the graph will become more steeper and steeper.
Yes. It adds up. And it does not add up linearly. You see, this is a non-linear add up.
Yes, sir.
All right, so this is a real world search example, and this is what we often do. This is a crowded scene, and you can ask this question: are there more females or males? Or you can ask another question: if you're looking for an old friend. Now, depending on what is the goal, my attention on the search mechanism is going to change. It's not always that I'm going to use feature search, or I'm going to use conjunction search, or any other kinds of search algorithms. Similarly here, if I'm looking at store, uh, if I ask this, does it have the brand Y you are looking for, versus does it have many organic green brands in the store? This is a specific question, and this is a more broader question. This is going to again change the way I look at it, or the way I search for information in this image. And what will happen is that when you have a more specific one, does it have brand Y you are looking at? This is going to be a more selective search mechanism, where you know what brand Y looks like, and you directly are able to not attend to a whole lot of the work. However, if you ask this question, does it have many organic brands in the store? That's a tricky one, because that will require us to run through the whole store. So you can't really use a very focused search algorithm for this. There's a third kind, which was given by Andy Treisman, and then improved by Jeremy Wolf from MIT, Princeton is Princeton. It's called the feature integration theory. So there it says there are two things that we do. One, first one, we form a master map. So it is done very quickly, and it basically picks up the properties of the stimuli like color, size, shape, and you don't have to attend. That's why it's called pre-attentive. Not attending or not required to attend is called pre-attentive, which is before attention kicks in. So at that stage, we have to develop, or we do develop, this master map, and then we do something called a feature map, which is a later stage that integrates the attributes and dimensions that were picked up during the master map. And slightly later on, what happens is different properties of the object are encoded in specific feature maps. So I have to show an example of how that works. Here. So let's say we show this to this person. So first you show a brown circle and then a green square. Many of the times, if you show them in very quick succession, typically within 15 to 30 or 40 milliseconds, then people report to have seen a green circle. Any idea how this could be possible?
I think our mind perceives first the shape of the object and then the color. So it may be possible that when we are shown a brown circle and then a green rectangle, so we perceive that.
Yeah, so the word for it is called illusory conjunction, which means that you basically form a conjunction between this one and this one. And because this comes first, it stays. Because this comes last, it stays. Together, they create an illusory image, which is not what the initial image is, and that is happening because of feature integration. Okay, so first you form a master map, and then here. So first you form a master map, and then you form a feature map, which essentially integrates other attributes and dimensions for that image at hand. So if this later map, which is of formation of the master map, it gets built, then that explains why they come together in a form of a conjunction, and this is what you see. Of course, it is illusory, but that's how perception works. Mathematically, this looks like this. So here you have an image. First, this image gets factored into multiple feature maps. So color information, orientation, this is distance, size. These are different properties of this image based on 4 different feature maps. And each of these feature maps, first get created, which are called feature maps. And then you have a master map of an image. Now, if you look at it from the world's perspective, so the world is out there, you focus attention, so you select a sub part of the world. From there, you have multiple feature maps, based on what property is being coded for, and then eventually you have an image. So the master map here again um, is going to happen, or is going to happen parallelly, because it needs to pick certain specific properties and feed it to create the feature maps. And here the example of feature maps are color, orientation, size, and distance. This is one more example from real life. So this is a scene search task. Here the task is to find the blender, one single thing, and one single way a blender looks. So here it is. However, if you say find the cocktail, it becomes difficult because there are so many things which are of yellow. There's so many things which might be looking as cocktail, but you really did not find the cocktail, which is a conjunction search, because here you're searching for color and the object, whereas here you are just searching for the object. To remind y'all, feature search is an example of this, where essentially you have this this black spot which pops out because of the gray spots, and you only look at what's black. Whereas for conjunction search, you look at let's say a black square, which is going to be difficult because you have a whole lot of them. However, it's also true that depending on how many items are there as distractors, your search size will go, search time will go up and down. Now there's a third or fourth.
Sir?
Yeah.
Sir, in the previous slide, can you move to that?
Mm-hmm.
Sir, does searching also involves that we prefer to search at those places first that the object is found, most probable to be found? Because suppose I
yes.
hang the blender from the roof, then it might be take a little longer time to search, or such it can happen, right?
Yeah, absolutely. You are 100% right. In fact, that is what cannot be explained by this model. Now, how do you explain why, if you keep the blender here, which is in its appropriate position, we are faster compared to if you keep the blender on the floor? Right. So that is why a different model was proposed, which is called the guided search model, where this is pretty much what you said, but it has a mathematical representation of it. They create what they call an activation map, which is representation of visual space at locations that represent likelihood of the location containing a target. So eventually you have different likelihood frequency representations that code this image. In the initial processing phase, you are only going to look at basic features like what we said, only your visual, your optic nerve, your visual processing area in the brain, and then create an activation map of the whole stimulus. Each item has its own level of activation. Now then search for the target based on the peaks of activation. And if the target generates an efficient search, essentially is going to happen if the target generates the highest or one of the highest peaks of activation. This is completely abstract, so let me show it how it looks like. So here you have an image that you feed in. This is, by the way, a computational implementation of this search algorithm, conjunction search, using using saliency map, which is as it's called. So here this is an image that you feed in, and the task is search the black vertical bar. Okay. So the black vertical bar essentially is here, right? How do I search it computationally? So here's the algorithm. Number one, you look at basic features and create an activation map of the stimulus. Two basic features. One is black, second is vertical. So first, I search black bar. Wherever there is black bar, it has higher activation. So the saliency map, which is an intensity map, codes where in this map one of the properties that I'm searching for exists. because it's a black vertical bar, this is a conjunction search. It has to be black and it has to be vertical. So first, I codify where are the parts where I see black and create a saliency map on intensity based on the black bar. That's why you see all of them are activated. Second, I search where are the vertical bars. So anywhere where the bars are vertical, that gets activated. So again, I have a saliency map based on direction. Then I add them up. And if you add them, this place, because it's an obvious thing, right? So you have this function and you have this function. Saliency functions, if you add them up, you have higher saliency, and you have the eventually the final saliency map. And here you see the black vertical bar here and here gets added up, and this place gets the highest intensity, and this is the place where you attend. So this essentially is a model of attention when you are doing conjunction search based on formation of the saliency map, implementing the guided search model computation. This is even more details if any of you are interested. Yeah, you have a question?
Yes, sir. Sir, previous slide. Yes, sir, this one. Search the type of question which is asked. Does it also affects the trigger that will be initiated first, like the search the black vertical bar, and instead we ask search the vertical black bar? Will the two processes be processed differently?
In this model, no, because there is no priority. They are just adding. So there's no weight. There's no weighted addition.
Okay, sir.
But it could. You're right. But in this model, they disregard that. Yeah. Now, if you want to look at even more details, so this is the basic components of guided search model. So here you have the stimuli, and then you break it up into multiple input channels, because that's the first step, initial processing. So you break it up into multiple input channels. You can break it up based on color, on orientation, and other kinds of attributes depending on the task at hand. So you have this RGYB color based channels. You have orientation, 0 degree to 45 degree, and likewise, and other stuff. Then you create feature maps. So feature maps can be happening bottom up, the black, vertical, like this. It can also have top down, something which you were just asking. So it can activate certain things. Now, if you then say, well, it depends on when it occurs in my task. If black vertical occurs, then I'm going to attend to black first and vertical second. Then you can have some weight associated to black or the feature map of black. If you don't, then you're having different kinds of attributes. Activate black lines, lines, and each of them build up your feature map. And obviously you have different activations based on the feature map. Eventually, the successful search is when you pick up whatever is highest, or if there are two and there is a tie, then either of them, which shows your highest activation level. If it's an if it's a wrong search, then you will end up creating a high activation area in your activation map, which is going to be a mistake. Or if it's predictive, then you have created a high activation area in a map. You expect it to find it there, but you don't, which again is going to either slow you down or going to create an error in the task.
Sir,
Yes?
in searching anything, just like the black bar, we will focus parallelly on both the things, black and the bar, vertical
Yeah.
black bar. We focus on all the features parallelly or one by one.
Yeah, so people have divided on that actually. It's cannot happen parallelly, because we know that in conjunction search, our search time goes up depending on how many attributes they add. So clearly there is some bottleneck. If it be completely parallel, we would not have any bottleneck. Right? So there is not complete parallelism in search. Now, whether there is something which gets searched first compared to second is something which is not very, I'm not very sure about it, because we have different results on that. But we do know that it's not completely parallel for sure. Otherwise, you will not have a growing function of time like here. If it would be parallel, you would have straight line. In fact, when you have three feature search, it becomes even more asymptotic. So automatically, it shows that it's not parallel. All right. So now if you look inside the brain, you will, and this is an fMRI image, it will show you that there is a large, this is the back side of the brain. You are seeing it from the top, by the way, like this. This is the front side. This is the front side of the brain, and this is the back side of the brain. And this area is the primary visual cortex. This area does get activated a lot. And here you see that there are other areas, including not just the visual area, that is also activated. So again, to show that if you do look inside the brain, you will find that multiple areas, including the parietal and the motor and the visual, of course, visual is more strongest, but there are activations of other areas of the brain also when people do these kinds of search tasks. I just want to stop here by giving you one example of a real world search. So this is when a doctor is searching for a tumor in a head. This is a scan. And if you have to search for and make a judgment about whether this tumor is bad or this tumor is fine and kind of benign and you don't have to worry about it, this is a great example of studying conjunction search or guided search in real action in medical domain. And now there's a lot of AI work that's happening in the area of medical AI, especially in image processing, where they are trying to automatize these kinds of things, as you might very well know, using neural networks. So which means that we now have a pretty good understanding of search to be able to not just study humans, to also develop computational models, and to also study doctors in action, maybe using eye trackers to see where the doctors are really attending to when they're making these judgments, and also build computer programs that are able to do the same task and say whether the tumor is good or bad. So that shows how psychology is integrated now with neurological apparatus and also in computer science and computational stuff. And that is only possible when we are understanding psychology in enough detail, not using random abstract words as is used many a times in psychology, and filling out these details as much as possible for us to be able to explain it, understand it, and even model it in all its intricacies, or as much intricacy as possible. And search or attention or perception is where maximum work has happened, which also means that is some area that we have understood much better than many other areas like memory or a lot of social psychological stuff is not yet been able to model, but we don't understand them in enough detail, or we don't talk about them in enough detail for us to be able to model it, though very, very recently some attempts have been made to understand the neurological basis of social decisions and judgments and cognition, and very little work in computationally modeling it. But if you look at it hierarchically, the maximum amount has happened in perception and attention. That also means a lot of how psychology has moved from commonsensical, oh, if I see it, I understand it, to a much more deeper scientific exploration to be able to actually have computer programs to simulate these kinds of searches that experts like doctors do about brain tumors, for example, using these kinds of models. So you can study this as a psychological question about what is it that people attend to when they search for a tumor in a scan. You can also build a computer program to be able to search for a tumor in a scan, and then perhaps also see how humans figure out whether that tumor is bad or good, and then try to see if you can build an AI which is also able to say whether the tumor is bad or good. Yeah. So I leave you there with these kinds of thoughts to think for. If you have any questions, we can take a couple of quick questions, but I still stop here. And if, of course, if there is no questions, then we can leave.